In this video, we're asked to find, yet again, the radius and interval of convergence of a power series. We've got terms that have n factorial x to the n in the numerator, and then terms that are factorial-like in the denominator, except that each factor goes up by 2 rather than 1. This is a huge clue that we want to use the ratio test, by the way, because we've got many factors, and the ratio test will allow us for the possibility of canceling many factors as we're doing our limit here. All right, so limit of the absolute value of consecutive terms. And again, we'll put the pieces together that match. N plus 1 factorial over n factorial matches. X to the n plus 1 over x to the n matches. And the products in the denominator matches. So let's concentrate on the factorials first. N plus 1 factorial is n plus 1 times n factorial, and that'll be over n factorial then. Notice we're talking about doing consecutive terms, so this is when we put in n plus 1 for n. Well, we still have the first n terms in there. The next one will be 2 times the quantity n plus 1 minus 1, which is where this 2n plus 1 is coming from. The 1, 3, 5 up to 2n minus 1 will go to the numerator, and we'll have the 1, 3, 5 up to the 2n plus 1 in the denominator. Now we cancel. The n factorials cancel in the first term, so we just get n plus 1. Everything except for the 2n plus 1 in the denominator cancels in the second fraction, and then we have absolute value of x in the third one. This behaves like n over 2n, or 1/2, as n gets large, so the limit here is 1/2 absolute value of x. Solving for the ratio test says that we need this less than 1. Solving for absolute value tells us that the absolute value of x has to be less than 2, or the radius of convergence has to be 2. The power series was centered at 0, so our endpoints of convergence, endpoints of the interval of convergence are plus or minus 2. We put in 2. We get that n factorial times 2 to the n over the 1 times 3 times 5 times 2n minus 1. These terms are certainly greater than, if I change all the 1, 3, 5 to 2n minus 1 to 2, 4, 6, and 2n. I've made the denominator bigger by a factor of 2 to the n. Okay. Notice that I could factor off a 2 out of each of these things. This is 2 times 2 times 2, n times, with a 2 to the n, which leaves me 1 times 2 times 3 times up to n. That's n factorial. This cancels and makes a 1 here. Okay? So these terms, without the negative sign, doing the absolute value of the terms, whether I plug in 2 or negative 2, when I do the absolute value of the terms, these do not go to 0. So it doesn't matter if I plug in 1 or negative 1, the terms in the series do not go to 0. That means that the series will diverge at both endpoints. Okay? Now again, the reason why it works for the negative is because, remember, in order for if the absolute value of the terms does not go to 0, then the limit for the original sequence cannot exist, because you got some of them that'll be positive and some of them will be negative, and they're not going to 0. All right, so neither endpoint will have that generates a series that goes to 0. Excuse me, that converges. I mean, they will both diverge because the terms don't go to 0. So our interval of convergence is just the open interval from -2 to 2.